So this is one thing. And why I have a few things keep doing this. And then now we want to know a few things. First of all, what is a drift current? Drift current is the current due to electric field. This one is easy to understand. You have an electric field, you drive me, right? So what is that? I equals to Q times the density times the velocity. And what is the velocity? Can someone tell me how you relate velocity to the electric field? We learned that last time.
The mobility times electric field.
Thank you. Is equal to mobility times electric field. Now tell me, what is mobility related to the potential? Sorry, what did I say? What is electric field related to potential? We just covered.
Negative gradient.
Negative gradient. Right, you see how this change, right? Now there is one problem in my equation. Do you think my equation is correct? I equal to Q and V. Think about this. I have an electron going this part. Does the current go from left to right or right to left? When the electron go from left to right, does the current go from right to left or left to right?
Right to left.
Thank you. Right. Sorry if it's too easy for you, but we need to be careful, right? So I was wrong. I need to put negative because when an electron go to other part, I need to make the current negative, right? So this is Q and mu dV dx, which is okay. Just think about this. If I have a high potential, right, for example, 5 volts, and then 0 volt, where does the electron want to go? It will try to go to this side. Did I have any typo? Right, so this is electron, right? It will go to the left. So you actually have a current going to the right. Okay. Then dV dx should be 0 in that case. What did I do wrong here? Anyone can point out my mistake? This equation should be correct. Yeah, this is correct. Sorry. Oh no, electric field is D. Okay, let me take care about that later. Somehow I kind of current of electron, right? Going from velocity of electron. Like if the electron goes to the right, then the current is going to the left, so it is negative. But velocity is mu times E. And E is negative dV dx. So if we have this gradient, dV dx is negative. Then the current should go to the right. Sorry, let me fix the, I think I might do something wrong, okay? But let me introduce another component, right? This is due, another is so-called diffusion current. It is due to the gradient of electron. Even you don't have electric field, it's due to the gradient of the carrier. Even if you don't have electric field, they will diffuse from somewhere. For example, if you have a lot of electron, very high density, and some of them, this is low density, I will have a diffusion current, right? The electron will go there. Of course, then it is opposite. The electron diffusion current is going in this direction. Is that okay about this diffusion current?
Professor, on the drift current, does the current go opposite of the electric field, or is it in the same direction?
It should be in the same direction.
Okay.
Right. But now I have a problem here. I kind of this one is showing it is going into the opposite direction. Okay. Yeah, I will fix it. I'm sorry for that. I will go back to you. Somehow I got lost. I don't know why the sign is not correct. Okay. Now drift current, it depends on one thing. Okay. It depends on the charge and something called diffusivity. Just like it depends on mobility. And now the driving force is the gradient of the electron instead of the gradient of the potential. Right, try to compare this. Gradient of potential, right? Or maybe I should do here. Gradient of potential, gradient of electron, diffusivity, mobility, right? So you see that they have some connection there, right? Let's see if this equation is correct. I have a higher density here, so electron will go to the right. Then the current will go to the left. But what is the gradient? Gradient is reducing, right? So this is negative. So that is correct because the current is pointing to the left, which is negative, right? So that's how you get the electron, the current. And here actually I was not accurate enough. Instead of current, this one should be so-called current density. Can someone tell me what is the relationship between current density and current? Current density equals to current divided by unit area. Okay, so your current, you have a lot of current flowing, but it depends on the area that you flow through. So that is the current density. So I hope you be careful when you're doing this. Unlike me, I just keep writing I, which is incorrect. I should say current density. Okay, so it is 45 already, but we are almost done. But I will just stop here. Let me fix this sign. I don't know what I did wrong yet. But remember, we have two types of current in the semiconductor. One is drift, one is the diffusion current. Okay. Yeah, so you can leave now if you don't have more questions. Something called Einstein relationship. Just now I say that I have a lot of electron here, very few electron here. Very less dense electron here. Can someone tell me again what happened when these two gas, electron gas, they are brought together?
The area with the more electrons, so the more dense, is gonna go move over to the less dense one.
So it means that I have a electron diffusion to the right, correct? So it means I have a drift current, a diffusion current to the left. Can this keep going forever if I don't do anything? If I just apply, let's say, zero bias to this system, can I keep diffusing electron to the right forever?
No.
Why?
Because if there's zero bias, so there's like nothing, you're not adding anything, it's gonna end up being perfectly balanced. And when it's perfectly balanced, there's no real diffusion to notice.
Very good. You said perfectly balanced. What do you mean by perfectly balanced?
The electron density is the same.
Oh, it's the same. Okay. So I forgot to tell you also, at the background, it has some positive charge because the electron comes from the ionized dopant. Okay. So at the background, I also have some positive charge and then plus a negative electron. So at the beginning, they are neutral. At the beginning, they are neutral. Okay. And now the electron keep diffusing to the right. It becomes this.
Oh.
So what happened now? Very good, right? So we start with a neutral charge because it's in our solid state system, it's difficult to have a net pure electron charge, right? So what happened? Can you tell me again? Would it still keep diffusing to the right?
No, because so I'm assuming if you're bringing two parts together, it's kind of like when you do a PN junction, where like there's this built-in electric field that you can measure from like in the depletion left, because it's a different charge.
You are right. Built-in electric field. Eventually, when I move electron to the right, this part becomes more and more negative because I have more electron. This part becomes more and more positive because the electron left, right? So what happened? As you said, a field will build in. You start have an electric field going from left to right. Then what happened? Electron under this electric field will try to go to left or go to right if I have this electric field.
It would drift to the left.
Drift to the left because electron feel the electric field. And that it means I have another current going to the right due to drift. Okay? Eventually, maybe I should say at equilibrium, I drift equals to I diffuse. Okay? Just, I have a lot of electron here. I keep diffusing to the right, but eventually I build up the electric field. It forces me back. I want to go there, but there's a force pushing me back. So there will be no current flowing, right? And from here, we derive a very famous thing called Einstein relationship. We remember what is I drift. Negative Q n mu dV dx. Sorry, I say it wrong, right? This is diffusion, right? Not drift, right? This is typo. What is the diffusion current? N d dn dx. Okay. Now, if we go back to our just assume Boltzmann statistic, right? This one I did not teach you. You learned in earlier classes. if you don't know this one, it will be good to review. We know n equal to n0 exponential negative E minus EF divided by KT, right? This is talking about the electron concentration as a relationship to its energy and the Fermi level. And actually, this is like the conduction band, I should say. Right? This is like the conduction band. Okay? Now, because it's equilibrium, do you remember when I say equilibrium, 0 voltage? What happened to the Fermi level? Is it constant or is changing? This is something I want you to memorize. When it's 0 bars, what happened to the Fermi level?
What do you mean by changing?
I mean, if you plot it on the space. So if you draw the Venn diagram, is it a constant or it can go up, go down? That's why.
Okay. Oh, okay.
Constant.
Say again. Who just said that?
Fermi level at 0 bias is constant.
Constant, right? Constant. Why I want to say that? Because if this is constant, then it means df, def, dx equals to 0. Okay? And this is useful because it helps us to do the differentiation, because we do need dn dx here. We have a dn dx here. Okay? So this one, because of time, we can do it quickly, right? Now you only the EC, the conduction band can be changing. So if you do the differentiation, you get EC divided by KT, right? You take this, no, you don't take the EC out, right? You don't take EC out, right? Because this is exponential, and then we just write the whole exponential term as usual, right? You differentiate an exponential function, then you will get this, which is just simply n divided by KT, because this whole thing is just n divided by KT. Okay? And of course, I missed one thing. From here, I should still add dEc dt. Is a chain rule, right? Because we are differentiate dx. We are differentiating with respect to x, not EC. Okay, so then we substitute back to number 1. It tells us that Q n mu dv dx equals to negative n over kt dEc dx. Is that okay? But actually, dv dx is just equal to dEc dx. Because this is the potential, right? When we draw the conduction band, right? This is telling us the electric field. The change of dE dx is just the change of the electric, just the electric field, right? Negative, right? So these two terms can be canceled. And I think I missed one important thing, right? I need to also put back the D here. Sorry for that. Because the current is actually ND dN dx. Okay, so I need to put here. So I keep copying the wrong equation, right? This is Q. This is QD. QD. Okay. So from here I copy the wrong thing. This one should be Q also, not N. This is QD, okay? And now I need to put back this QD here, right? So now you see dV, dx, dEc, dx can be canceled, okay? And then N can be canceled, Q can be canceled. You come up with something called Einstein relationship. KT over Q equal to D over mu. Now, it's very easy to memorize. You just memorize this as the it rhyme with each other. Q and mu, they rhyme with each other. KT over Q is a constant you always play with. And now we want to relate KT over Q to the diffusivity and the mobility is D over mu. Okay, so you find that somehow the mobility has a relationship with the diffusivity. Okay, we cannot see from here, but the Einstein relationship tells us that diffusivity divided by mobility is KT over Q. If the temperature is higher, the diffusion term actually is stronger. Now, if you go to zero temperature, your mobility is much more important. So drift velocity, the drift current will dominate. If you are at a very high temperature, the diffusion component will dominate. Okay, maybe a little bit messy also because I'm sorry I copied the equation wrong, but the most important part here I would like you to take home is KT over Q equal to D over mu. I hope that you remember this relationship. Second thing is, I hope you remember that there are two components of current, drift and diffusion. At equilibrium, they are the same, right? And I hope you appreciate how to calculate the drift and diffusion current. The drift depends on the electric field, the change of the potential. The diffusion current depends on the gradient of the concentration, which are all very intuitive, right? Like you have two class, right? You have two professor, maybe let's say one professor, the same class, right? One professor, you like one professor, let's say teach better, right? Then all the students try to go to that professor. But then eventually they set up a system saying that if you come here, you need to pay extra. Then that is the electric field. It pushes you back until it becomes an equilibrium. Okay? Any questions about this? No question? Okay, then why we want to study this one is that as a device engineer, I really want you to memorize this, right? It's okay if you cannot follow the derivation, right? But this is a must. KT over Q equal to D over mu. Because when you memorize this, you know that how the temperature related to the diffusivity and mobility. And why you care about diffusivity? Because diffusivity is diffusion current is an important component in device. So now when you think about device, you have to have the picture in your mind. Oh, there's drift current, there's diffusion current. I cannot try to explain a device just by working on the drift current. And okay. Now then, how do we model a device? We basically capture everything already, right? So here we are trying to introduce something. Then what is the total current? Total current is equal to the drift current plus the diffusion current, correct? Right? It's just that when it's zero bias, there's no current. Drift and diffusion current are opposite to each other. Here, actually, I make a mistake again, right? Even in my cheat sheet, where at equilibrium, should the drift current equal to diffusion current or the drift current equal to the negative of diffusion current? Look at this. Should it equal or equal to the negative at equilibrium?
Negative.
Negative, yeah. They should add together to 0. So here, I'm sorry, I again miss a negative, right? And because of this, this has to be negative. Okay? And then this has to be positive, right? So I did make a mistake, and actually here should be negative, right? Because the conduction band is the energy seen by the electron, right? So for example, let's think about this. Here, the electron is going to go down, right? Then it means electric field is going from right to left. Right? So that electric field is going from right to left. Then if you just look at the DEC dx, right, it has to be negative. Is that okay? Okay, so this one gives you some, the reason I found the mistake is because now I'm talking about the total current, right? Total current, when it is equilibrium, when J equal to 0, means it is equilibrium. It means J drift equal to negative J diffusion, right? Just like previous slide. Is this clear? I think I confused you, but is this clear now? Total current. This is the total current. Is that okay? Now, because of this, I can write this as this one. Qn mu dvx dx. This is the drift current. Let's compare to here, right? This is the drift current. And then for diffusion current, it is Q dn dx. Okay. And eventually, right, I'm not going to show you, right? If you're interested, let me know. We can write this as this equation, Qn mu d phi f dx. We introduce a quantity called Quasi-Fermi level, Q phi f. This is not the real Fermi level, but it's the so-called Quasi-Fermi level. The reason we could do this by using the Einstein relationship, right? Because you see that D disappear here. The D is no longer here, right? But the reason is because we use the Einstein relationship. And then we just use this equation, n equals to this one. We do the differentiation, we get the KT over Q. You plug in, then you are able to take the whole thing out. And then we can just say that, hey, the whole current is due to the quasi-Fermi level. Now, I don't think about drift. I don't think about diffusion. I only think about this. There is a quasi-Fermi level. If this is constant, the Fermi level, if it is constant, then there's no current. If there is a slope, then there is current. Any question about this?
Professor, this is a quick question.
Yes.
In the equation of the current, that's the mu for in general, right? For both NMOS and PMOS.
No, the equation here is only for N type, for electron. Probably you want to ask, is it for electron or hole? This is only for electron.
Oh, so the I was talking about the mobility term in there, the mu.
Huh?
Does that the mobility, the mu?
Yeah.
Does that refer to electrons?
In this case, it's for electron, right? If it is for hole, it will be different. Think about hole. It goes in the opposite direction. So
plus and minus,
this one becomes plus.
and the other one minus.
The other one for this one is this one becomes minus. Yeah. Actually, I forgot we need to derive, right? Let's think about this. Let's think together. If you have a positive charge here, right, and then negative, you have the electric field, right? If you have a hole, what happened, right? This is for electron. What happened to the hole? It's going to this side, correct? And then, so you actually have the hole going to the right. However, how about the potential? Potential is negative. dVx dx is negative, right? So actually for hole, this is still negative. But for diffusion, it's different. If you have a lot of electron here, you have less here, it diffuses to here, right? dN dx is positive, right? So your hole is going from here to here. So this is a positive hole current, correct? So actually, this one is still positive for this one, but maybe this one becomes positive. Let's check again. The voltage current is going from here to here, right? And your potential is actually smaller than 0. Then I got confused. I think one of them have to be swapped. dV dx, electric field go from here, so dV dx is positive. Then the hole go from left to right. So we have a positive current. But why do I say this is positive? This is negative. The hole go from here to here. So dV dx has to be larger than 0. I mean, dVs is smaller than 0. Oh, okay, so I'm right here. I'm wrong here. What is dN dx? Can you tell me what is dN dx here? Is it positive or negative? I have a lot of hole here. Very few electron here. Is it positive or negative? Does the concentration increase when you go to right or decrease? The concentration becomes smaller when you go to the right. So dN dx is negative. Am I right?
Are you referring to the concentration of electrons?
Of hole, sorry, here we're talking about hole. The concentration
It would decrease.
is higher here, right?
Yes, it would
So
decrease.
it is negative, right? dN dx, right? Because we set the right to be positive direction, right? So it becomes smaller. So dn dx is negative. But your hole is going from left to right, so your current is also going from left to right. So that's why its drift term is negative q dp dp dx. Maybe I also use the wrong symbol. I should use dp, will be less confusing. But for the drift part, it's still the same. Negative qp mu d dv dx. And this is the total current, right? So this is positive, it becomes negative for hole. Diego, does that make sense to you? Do I answer your question?
Yes, I'm trying to digest this. Yes.
Yeah, so you see, very confusing, right? I also make so many mistakes when I'm teaching. I'm sorry for that, right? But I hope that you also see that all you need to do is to sit down step by step. You really cannot guess, right? To look at each term and then to determine the direction. Of course, you can just write it as a cheat sheet, right? I'm not going to ask you to derive this equation in the exam. But the point is, in the future, when you try to analyze your device through intuition, you need to understand all these things. Remember how they travel, and then the electron flow is the negative of the current. Okay? Now then finally, then I want to tell you another equation, the so-called continuity equation. You don't need to derive, but nothing to derive, right? It's just telling you how they solve the equation in TCAD. Basically, this is what it says. If I have a box, right? And then in this box, I have current going out, J, right? I can have current going out. They are leaving this box. And this is represented by so-called the divergence of the current density. Okay? So if you keep having something going out, you need to have a source, just like water. If you have a water keep going out everywhere, right? For example, if you look at this box, and if I have water going in, water going out, like this, you will find the divergence of J equal to 0. It means that there's no net molecule going in or leaving the box. Okay, but sometimes they can be non-zero. Why? Because you can have generation. How can you generate electron in a box? Any idea? This is a typo. Should be recombinant. This is generation. How do you generate something out of nowhere? How do you generate something? Anyone? How suddenly you create an electron?
You energize the atom.
Energized atom. I think you know what you're saying, but the keyword, what I'm looking for is you have energy, right? You create electron hole pair, right? Just like what you said, energized atom. What you're trying to say is you excite the electron to the conduction band, and then you leave a hole here. Okay, so that is the generation. Now, maybe can you also answer me? Then how come we have recombination? What does it mean? It means that some electron disappear. How do I remove the electron? Right, you're just saying that I keep have a electron going into that region. How does it recombine? Any idea? How do I remove the electron or a hole? Maybe what you said is the opposite. The electron and hole, what happens if they recombine? they becomes energy. It can be a light photon, or it becomes through some special process, it can become the vibration photon, but electron and hole disappear. Make sense? And then with this current divergence and also this generation and recombination, the final is tell you the rate of change of the carrier, how it is changing. So this is no rocket science, right? It's just a common sense. I have a box. I keep putting some particle into the box. I cannot put forever. In a steady state, I cannot put forever. There must be some mechanism to remove the particle. Otherwise, my box is going to explode. Okay? So the whole device physics is captured here. You solve the Poisson equation, and then you solve the carrier continuity equation. Then basically you solve everything. And that's why in TCAT, you see that it say couple, Poisson, electron, and hole. Now, can someone guess what is the meaning of this three keyword in TCAT? What's the meaning of Poisson?
Solve the Poisson equation.
Solve the Poisson equation. And what's the meaning of the electron?
The electron continuity, I guess. Equation.
Thank you. It solves the electron continuity equation. And similarly, you need to solve for the whole continuity equation. You solve this three equation, you solve the whole system. Then you can predict how the device operates. Is that clear? Any questions? If no, we are done with the transport. We are done. A lot of stuff. Also, sorry, somehow my performance is not good. I keep making mistake. But really doesn't matter if you spend time, try to understand. Actually, I hope my mistake actually help you to understand better why I make those mistakes. It's all about the sign, plus minus, plus minus. But most important is remember you have the Poisson equation, carrier continuity equation, how to calculate the drift diffusion current. You understand there are drift part, a diffusion part. One is due to the electric field, which is the gradient of the potential. Another is due to the gradient of the concentration. And that is everything, the basics. Okay. And in principle, this can answer all the questions you encounter in EE122 or EE221 in principle. Of course, you need to solve this differential equation. Some cannot be solved analytically, right? But there's everything about that, almost. And that's why TCAT can simulate arbitrary device, because this is the physics. Okay. So if no question, I will move forward. We are done with the transport, right? Now I want to talk about short channel effects. This is very important. And I already uploaded all this paper. Please try to read them if you have time, right? Including the